Okay. Good morning. We are going to try to talk about the 3.1 Solve Linear Systems by Graphing notes today while I'm out. So please try to take these notes on your note sheet and so that way you can attempt to do the homework. This is still review from Algebra 1. We're going to be solving linear systems by graphing. So first let's talk about a system. When we talk about a system of two linear equations, they're basically two equations that can be written in the form ax plus by equals c and dx plus ey equals f, where x and y are variables. So these can be written in slope-intercept form too, but basically these are two linear equations. And we're going to solve these graphically today. And when you look at a graph, the solution of a system of linear equations is where the two lines intersect. So we're going to be looking to see where those lines intersect. And so one example is of something that can happen is if you have one solution, and you don't have to color code this, but here I have this line and this line, and notice that these lines meet in one point. So notice that when we graph it, these lines intersect. And so we have one solution. In order for the lines to intersect, the slopes have to be different. And in your text, it asks you to name systems as with different descriptions: consistent, inconsistent, dependent, independent. And because there is a solution, we say this system is consistent. And because there is one solution, we say that this is independent. So one, independent. Okay. Another possibility is for us to have two lines that don't intersect. So we know that those lines are parallel lines. So if we graph and we see lines that are parallel, then we're going to have something that has no solution. No intersection, no solution. We know that to have parallel lines, the slopes have to be the same. But in order for them to not meet, the y-intercepts have to be different. And something that has no solution we just call inconsistent. So that system is said to be inconsistent, no solution. Now something with infinitely many solutions, it looks like this is just one line. But in reality what's going on is that it's like one line is graphed on top of another one. So some textbooks call this lines that coincide, but a lot of us might say overlap, even though it's areas that overlap. Anyway, either of those is okay. And because it looks the same, the slopes have to be the same, and the y-intercepts have to be the same. And so we say that this system is consistent because it does have a solution, and dependent because there are so many solutions along that line. And every point on that line is a solution. So the way we'll do these problems is that it says to graph the linear system and estimate the solution. And so to do that, we want to graph these different systems of equations. And notice that these are in standard form, but what we would want to do is put them into slope-intercept form. So we'd want to make sure to isolate y first. That will help us. For sake of time, I'll do this for you rather quickly. So in this first one, I would add 4x and then divide by -2 to get y is -2x plus 6. And I could graph that by going down to, going to 0, 6. And then going down to over 1 because of my slope. And I think it's a good idea to plot as many points as you can here, because we're looking for where they intersect. So we want to make sure that our line is nice and straight. And so those points can help us. So we put the first equation into slope-intercept form and graphed it. Now let's do the same thing to the second equation. Here I would subtract 4x and divide by 8. And I get that y equals -1/2 x minus 3. Make sure you reduce your fraction. So I'm going to plot my y-intercept at 0, -3, go down 1/2, and I can see that nice intersection right away, right at here at this point, but I still should connect, because it did ask us to graph the system, so we want to graph each one. And now that we have that, we can look to see where they intersect, and we can see that this intersects at the point 6, -6. And you can always test your solution by putting it back into the original equations. So for example, if I put 6 in for x in this first equation, and -6 in for y in the second equation, notice that I get a true statement. The same would be true if I put that in the second equation. If I put 6 in for x and -6 in for y, I still get a true statement. You don't have to do that, but it's a nice thing to do, especially in a quiz or test situation, so that you can check what your answer is. Okay, so we could do the same thing in example 2. This one is pretty easy to isolate. This is just, we're just going to add x, and I get y equals x minus 7. So I'd have a y-intercept of 0, -7, and that's a slope of 1, so I can go up 1/1. And then we'd isolate y in the second equation also. So you'd subtract x, divide by 4, and at the end of the day you get y equals -1/4 x minus 2. So we'd have a y-intercept of 0, -2. Again, go down 1/2. Did I not count right? Oh wait, go down 1/4, -1/4, sorry, go down 1/4. 1, 2, 3, 4. And we can see that's where, ignore that one, that's where they're going to intersect. And we can see that this is at the ordered pair 4, -3. And we could check and see that that is a valid solution. Okay? So both of these were examples of graphs that had one solution. Okay? Notice that they had different slopes, and that's why they intersected to provide that one solution. It is sometimes possible, however, for us to have equations a system that has no solution or infinitely many solutions. One thing I want to say about infinitely many solutions is that do not say all real numbers, because it's not all real numbers. We're looking for ordered pairs that make it true, and not every ordered pair is going to make it true. It's just all the points on that line, the infinite number of points on that line, and that's why it's infinitely many solutions. So let's get out your calculators, because now we're going to talk about how we can solve a system of equations on the calculator. And to do that, what we'll do, and we won't do all of these together, what we'll do is to do that in the calculators, we want to put each equation in slope-intercept form. We'll put them in the calculator and then graph in the calculator and see where they intersect. So let's just do step one. It says solve each system of equations on the calculator. So what I would want to do is isolate y. Now for sake of time, I won't show all the work. I hope that's okay with you guys. But this first equation right here turns out being, if you trust me, y equals 3x minus 10. And this second equation ends up being y equals negative 4/3 x minus 4/3. Okay? So do your steps to isolate y. Be very careful with your signs and reducing and all that. And then we're going to put them in the calculator. So in the calculator, what we'd want to do is we'd want to go to this button y equals. If you have anything in there, if you have anything in there, just clear it out. Make sure that any plots, if you have a plot that's highlighted, arrow up, unhighlight it. And now we're going to enter the equation. The first one is 3x minus 10. So we type in 3. X is right here next to the alpha, x minus 10, and press enter. And now we want to enter in y equals negative 4/3 x minus 4/3. I always like to enter fractions in parentheses just to be safe. And make sure that when you use the negative sign, that you use the negative sign under the 3, not the minus sign. So this is a negative 4 divided by 3 x minus 4 divided by 3. And now those two equations should be in your graphing calculators. Okay? Now to graph it, one thing you can do to get what's called a standard window is you can press the zoom key, and then number 6 says standard, and that gives you a negative 10 to 10 on the x and a negative 10 to 10 on the y. So if we hit 6, we should see those two equations pop up. Okay, so that was step 2. We want to make sure we see the intersection. Now we go to step 3, which is calc. To get to the calc menu, notice it's in a different color above trace. So we're going to hit second trace to get to the calc menu. And then we want to go to number 5, which is intersect. It then asks first curve question mark. We'll notice in the corner here it says y1 equals 3x minus 10. That's the first equation we want, so we hit enter. Now it says second curve question mark, and that's the second equation we want up here, so we press enter. Then it says guess. You can just press enter, or some people like to move closer to where the point of intersection is. And the third time you press enter, it jumps and it gives you that intersection. So we have that intersection at 2, negative 4. So again, you can just press enter, 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 but I wanted to give you the reasons why that was. So our calculator tells us our answer is going to be 2, negative 4. Okay? We're going to skip 4. And instead of your turns, I'll guide you through these real quick. I'm going to give you the slope-intercept form for number 5 for each one. In number 5, you end up with y equals 1/7 x minus 6/7 for the first equation. And for the second equation, we end up with y equals 1/7 x minus 6/7. What do you notice about these? They have the same slope and the same y-intercept. Those lines are going to be right on top of each other. So we say that this is going to have infinitely many solutions. It would kind of be silly to put that in the calculator, wouldn't it? Because they would intersect at every single point on that line. Now let me put 6 for you into slope-intercept form. The first one, I get y equals 2x minus 4.5. And if you did the work to put the second one into slope-intercept form, we'd get y equals 2x minus 3. Again, I don't expect you to do this in your head. I'm just trying to go fast so you can start your homework, okay? What do you notice about these equations? They have the same slope, but different y-intercepts. Those are going to be parallel lines. If they're parallel, they're never going to intersect, and we'll have no solution. Let me do the same thing for 7. The first equation ends up being y equals 1/8 x plus 7 over 2. The second equation ends up being y equals negative 4/7 x minus 5. Again, you can take your time to put them into slope-intercept form. Notice these do not have the same slope. So we're going to have to use the calculator in this case, because it says to find out where they're going to intersect. So let's do that. Let's go back to our y equals, and let's clear those equations out. And let's put the new equations in. 1/8 x plus 7 over 2. And negative 4/7 x minus 5. So we'd want to put both equations in, and then we can graph to see what that looks like. And if we when we graph, we see that the point of intersection isn't on the screen. Let's try to see if we're able to find the solution, even if we don't see it on the screen. Remember, we would do second trace to get to the calc menu, number 5, enter, enter, enter. And what happens is the calculator is searching on the screen for something, and it doesn't find anything. That's why there's an error. It doesn't mean that there's no solution. Always. If you look, it just means the solution's over here. The calculator needs to see it on the screen. Remember, we're using a window that has the x's from negative 10 to 10. Notice that it's over here. That means we need to make the x's smaller. To do that, you're going to press window, and window tells you what's the smallest x value that's on the left, the biggest one that's on the right, and then how the calculator is counting. So it's going by ones. And it does the same for the y-axis. Don't worry about the x-res. Well, we said that our x-min needs to be more minimum, so maybe we could try negative 15. And let's see if it shows up then. You can just press graph, and let's cross our fingers and hope it works. Hooray! We're able to see the solution. Now if we try this second trace, number 5 for intersect, enter, enter, enter. Now it jumps to the point because it can see it. Notice it's not pretty, it's not integers, but these are still values that we can record. So notice that here we had to adjust what's called the window. And our intersection was approximate. It was about negative 12.21. Oftentimes hundredths are a good thing to round to if they don't tell us. And the y was 1.97. And so I'm going to put about in my happy cloud so people know that that's just an estimate. Okay? So that's the gist of it. Basically, you're just going to be graphing equations and looking to see where they intersect each other. And we want to start talking about modeling. We'll talk more about this in the upcoming days. but the systems of equations are sometimes pretty nice ones to model. So this example says a business rents inline skates for $15 per day and bicycles for $30 per day. During one day, the business has a total of 25 rentals and collects $450 for the rentals. It wants the number of pairs of skates rented and bicycles rented. And so this wants skates and bicycles, and those are going to represent our variables. Those are the two things that we're looking for in our system. So I'm going to have X represent the number of pairs of skates, and Y represent the number of bicycles. And that can help us set up our equations. Oftentimes, it's helpful in systems, you guys, to look for a grand total. Do you see a number that represents a total? Well, one number I see that's a total is $450. So that is going to be our money equation. That's our grand total. Now, a lot of times people will just say, all right, well then X plus Y is 450. But notice 450 is representing money, and X and Y are talking about things. But notice it tells us how much money each thing is. The pairs of skates are $15 to rent, so I can make that the coefficient of X. The bicycles are $30 a piece, so I can make that the coefficient of Y. And now that is one of our equations. $15 for each pair of skates plus $30 for each bicycle equals $450 they collected that day. But a system needs two equations. So maybe there's another total. Well, this is also a total, this 25 rentals. So we can say, all right, well, how would we get 25 rentals? Well, what did they rent? They rented skates and bicycles. So we have X rentals plus Y rentals equals 25 rentals. And that would be the system of equations that we dealt with. Again, just trying to speed things up. The solution that we end up getting if we were to graph is 20, 5. But I'm not going to happy cloud 25 in a story problem. I want to say what it means. The 20 means I have 20 pairs of skates, and the 5 means I have 5 bicycles. So the only difference in a story problem is that we don't stop at the ordered pair. We just give meaning to it. So we would say 20 pairs of skates and 5 bicycles were rented. And that's my solution, okay? And on ePark 2, I do have, you know, the more of the work that's shown for you as far as the graph and what that looks like. But this is the essence of it. Again, this is review from Algebra 1. Then let's just set up example 9. So there's one more example you have for that setup. At an ice cream shop, one customer pays $9 for 2 sundaes and 2 milkshakes. A second customer pays $13 for 2 sundaes and 4 milkshakes. And then we want to set up and solve a system to find the cost of each item. So that means when I label the variables, that X isn't just sundaes. X is going to be the cost of a sundae. Likewise, Y will be the cost of a milkshake. All right. So now, if we look for totals again, one total is $9. And so if we look at that total of $9, what's happening is that these are costs, but notice that I have 2 sundaes and 2 milkshakes to make the $9. Another total I have is $13. That was for 2 sundaes, 2 X's, and 4 milkshakes, 4Y. That would give me 13. Now I have that system and I can solve. Well, for this one, I'll tell you that if you isolate y, you get negative x plus 9 halves. And in this one, we get y equals negative 1/2 x plus 13 over 4. So again, what you would do, even if we're solving on the calculator, is we would put those into slope-intercept form. Then we would want to put that in our calculator. So I'm going to go back to the y equals, clear the screen. And you don't have to do this with me. You can practice later if you want. I'm just trying to save time. Is negative x plus 9 halves, and then negative 1/2 x plus 13 fourths. Again, my fractions are in parentheses, just a habit I have. And then if I want to get back to that regular graph, remember I do zoom 6, and then I get that negative 10 to 10. And oh look, we can see the intersection. Remember, we do second, trace to get to the calc menu. Number 5, enter, enter, enter. And I get this, 2.52. So in this context, you guys, this 2.5 is the cost of a sundae. So we could say sundaes cost $2.50 and milkshakes cost $2. And that would be my final answer there. Okay. So just a reminder that my worked out solutions, not this one, but another sheet I have here, that's going to be posted on ePark 2. These video notes will also be posted on ePark 2 for you guys to get to. But again, hopefully this is review from Algebra 1, maybe not the calculator part, but the rest of it is review from Algebra 1 as far as the 3 types of systems, graphing to solve, being able to tell if we have infinitely many or no solutions, and even setting up and solving the story problems. The calculator part might be new for you. But hopefully this is enough information to get you guys started. And after talking about milkshakes and sundaes, I'm hungry. All right, you guys have a great day. I'll see you guys soon. Bye. And then press